Hi everyone. So in this video, I would like to introduce you all to our experience in fine-tuning a large language model to become an expert in DDR5 protocols. We are still pretty early into this project, but we already have a lot to share, and we think this project could have pretty big potential in the future. What we did can be rather easily applied to fields other than DDR5, such as other communication protocols or knowledge in general. So a brief introduction of myself. My name is Xinran Li. I am a hardware development engineer from FuturePlus Systems. I graduated from college not too long ago. My interests are primarily in hardware such as board design and system design. I am currently working on a DDR5 proposal board that will be used with a key-side logic analyzer to capture DDR5 traffic for data analysis. I studied a bit of machine learning in school a long time ago, and the recent trend in AI really caught my interest. I felt we could really use the power of AI to improve our work efficiency in working with DDR5. So we decided we should give this project a try and see how far we can go. Now I'll start going into the background of this project a bit deeper. So we know that the data rate of DDR5 has increased significantly compared to older generations. The current targeted end-of-life transfer rate of DDR5 is 8800 megatransfers per second, and that is more than double of the 3200 megatransfer per second max data rate of DDR4. In the future, DDR5 MRDIMM is going to double that as well. The massive amount of data is generated and captured when measuring the bus. It can be quite difficult when engineers are required to manually review and debug such data. It would be great if an AI can help discover questionable data patterns. Also, to match the incredible bandwidth, the protocols had also become a lot more complex. Here's the trend of the number of pages of different generations of JEDEC DDR standards. The spec of DDR5 DRAM is more than 500 pages long, twice the length of DDR4 DRAM spec. It has been getting more and more difficult to debug a DDR5 system or even just to learn about it. There are also specs for other closely related chips that one need to remember, such as the spec for the RCD, the buffers, and etc. This is easily thousands of pages in total, and that is a lot of information to learn and mostly to remember. Again, it would be wonderful if we can use the power of AI to help streamline the debug and learning process, and potentially also analyze the data directly. At this moment, I believe most of you have tried to talk to a larger language model such as ChatGPT at least once. They have shown truly remarkable capability in understanding, learning, and reasoning text information. A human user can easily talk to it in natural language and chat back and forth with it to learn about such knowledge. When used correctly, it could be a great teacher or a helpful assistant. So we started this journey in finding a way to make use of the power of LLMs to ultimately help us work with and debug DDR5. The current goal of this project is to create an experimental proof-of-concept system that is able to respond to a user as an AI expert in topics related to DDR5 in natural language, while also be able to analyze data captured by test and measurement devices. At this stage, we have fine-tuned a few models based on a pretty big portion of the DDR5 DRAM and RCD spec, plus some other relevant information we collected elsewhere. We find the current results to be quite convincing already, and there are still a lot more to do. Hopefully you can find our journey interesting and perhaps even useful. I will be going through some important basic concepts of LLM first. I think they will help you understand the process we went through a lot easier. Let me first quickly introduce the nature of LLM. A large language model is an artificial neural network that processes text inputs to predict subsequent text tokens. Tokens are the fundamental units of text the model recognizes or generates. You can think of tokens as words for the AI. LLMs often have a specific neural network architecture called transformer. You can see a typical structure of an LLM on the right. I won't go into the details here. There are some really good examples on YouTube that explain this architecture really well. Transformer models are especially good at understanding the relationship between sequential data and the importance of them in their context, thanks to the attention mechanism. It can easily understand complex literature, articles, conversations, and even programming code. This is because the tokens in these texts are connected by grammar, semantics, and logic. On the left, we can see this example has these three words as input. The sky is. When put into the network, it will compute the relation between each of them. Based on that, it will determine a list of fitting next word in the sentence. In this case, the most probable case is blue. There are four important specs of an LLM you can use to see how good it is. There are the context window, the parameter size, the training token size, and benchmark scores. First, let's talk about the context window of an LLM. In some way, it is similar to the short-term memory of us humans. It represents the maximum number of tokens an LLM can keep track of. For example, for a chatbot LLM, each time the user sends an LLM message, the entire chat history must be sent together to the LLM as the context. As the chat goes on, eventually the context will become too long and the model will either completely forget what happened at the beginning or start to output incoherent responses. As you can see from this list of popular LLMs, most have a few thousand tokens of context window. The reason the context window exists is very simple. It is because the model was only trained on that length of data. For example, for Llama 2, all the training data points did not exceed 4096 tokens. Also, this short-term memory, similar to humans, is not perfect. LLM often cannot recall the information 100% correctly. Some are better than the others. The information in the middle of the context is also the most difficult to recall. But again, this is quite model-specific. Some models can recall everything near perfectly, and some can only remember the beginning and the end. Next, let's talk about the size of LLMs. Their size is measured in terms of the number of parameters in the neural network. On the right is a very small and simple fully connected neural network to help you understand what is a parameter and how to count them. It has one input layer, one hidden layer, and one output layer. There are 3 neurons plus 1 bias in the input layer, 5 neurons plus 1 bias in the hidden layer, and 2 neurons in the output layer. Each connection here is one parameter, so in total we have 3 times 5 plus 5, 20 parameters between layer 1 and layer 2. 5 times 2 plus 2, 12 parameters between hidden layer and output layer. 32 parameters in total. LLMs, on the other hand, are much larger. Their parameter size ranges from a few billion parameters to hundreds of billion parameters. On the left is a table for the size of popular models that are widely used today. In short, when all the other parameters are controlled, usually the more parameters a model has, the higher performance it has. Another important parameter is the amount of data a model was trained on. Naturally, the more data the model has seen, the better it should be. LLM nowadays are trained on an unfathomably large amount of text data. Some popular ones as seen in this table were trained on trillions of tokens. The dataset not only needs to be large, but also needs to have good quality. A lot of the most cutting-edge research is on how to best prepare the data to most effectively train the model. For example, Phi 2, a tiny model made by Microsoft, featuring only 2.7 billion parameters, has performance on par with models multiple times larger, all thanks to highly organized and selected quality training data. In short, when all the other parameters are controlled, the more data a model is trained on, the better. And also, the better the data is prepared, the better. Benchmark results can also be very useful in determining the performance of a model. A very popular benchmark used to evaluate LLM is called MMLU, Massive Multitask Language Understanding. It is like a multiple-choice exam for LLM. It tests knowledge across many different subjects. Human eval, on the other hand, is often used to evaluate a model's ability in writing code, mostly Python code. Another popular one is GSM-8K, Grade School Math 8K. It is a set of math problems used to test the model's performance in mathematics. The number you are seeing in the table is often the percentage scores of the questions the LLM got correctly. You might ask, why not only look at the benchmark results to judge the performance of a model? The answer is that these benchmarks are open to the public, and those who train or fine-tune the model intentionally or unintentionally sometimes mix the questions and answers used in the benchmarks into the training data. This greatly distorts the results and makes the results useless. The industry is trying to come together to create a semi-open benchmark standard, but for now, the results of the benchmark scores are not to be taken 100% seriously. As powerful as LLMs are, they all have some common weaknesses. First, a well-known one is that the LLM often hallucinates. By that it means the model will often say nonsensical or incorrect information with a lot of confidence. These outputs are still in perfect human language with good grammar and spelling and such, but the information is all just wrong. Here is a good example of hallucination. I asked a model what is the purpose of DDR5 RCD, and it just gave me a completely wrong result. RCD is registering clock driver. The result might look somewhat correct to someone unfamiliar with the field, and in this case, LLM is that person, but instead of admitting they do not know what RCD is, the LLM writes a paragraph that it thinks look kind of correct. Other limitations include the fact that LLM often struggle with non-text data a lot. They can't really take images or sounds as input easily, and they often do badly against numbers, tables, figures, charts, and other types of data. I know some of the new cutting-edge models are adding image and sound as part of their input embeddings to make the model multimodal, and some are fine-tuning models on mathematical problems. But in general, these other forms of data are still quite difficult for LLMs. There are other kind of limitations, but these are some of the more important ones to us. Okay, now that we know the basics of an LLM, let's dive into the important part that everyone is interested in, teaching an LLM some new knowledge. We are interested in an LLM that knows all about DDR5, but the following information should apply to any domain-specific knowledge. So each LLM has some knowledge in all sorts of fields when it was pre-trained. Some really good ones like GPT-4 even come with some DDR memory-related knowledge. But when asked questions that are very specific to a certain domain, they will often start to hallucinate incorrect answers. This is called zero-shot prompting, asking a question without giving the model any extra information, making it rely solely on its past training. We tried this on many models and only GPT-4 was somewhat coherent. To improve the quality of the response and reduce the hallucination rate, we need to teach the LLM about what we want to know first. There are many ways of teaching an LLM and they all have their pros and cons. On a high level, there are two ways to teach an LLM. The first is called prompt-based learning. This is kind of like how you would teach a person. You will simply provide information and communicate with the LLM, teaching it the information in a conversation, explaining everything to it. The second way is fine-tuning. Essentially use more data that is oriented on a certain subject to continue training the pre-trained LLM's parameters. This usually needs only a small amount of data compared to the amount used to train a model from scratch. Let's first talk about the most straightforward prompt-based learning. The most basic way of prompt-based learning is, like I said before, just providing some extra context and extra information. Here is an example teaching an LLM how to do a multiple choice question. It is not super straightforward for the LLM, in fact. If you do zero-shot multiple choice question prompt, sometimes it might choose an option without explaining why, or answer the question with a paragraph but does not choose an option. The better way of doing this is called few-shot prompting. You can simply provide a few examples of multiple choice question, the thoughts behind solving the question, and the final answer choice. The LLM will have these as the beginning of the context for text generation. We will ask the LLM the actual question. It will be able to follow the steps used in the examples, show its thoughts, and select an option. Besides making the LLM do a particular thing, you may also want it to answer some questions regarding a specific topic, such as DDR5. In this case, you can just give it a bunch of information about that topic before asking your first question. You can put an entire Wikipedia page into the chat, and a well-trained LLM will be able to use most of that information to answer your question. But if you put too much information into the context, things will start to fall apart. This is the context limit I talked about before. There are some pretty impressive models with hundreds of thousands of context windows, but this is still not enough to fit just the DDR5 spec. Also, like I mentioned before, more often than not, context in the middle is more difficult to recall than context at the beginning and the end. This is referred to as the lost in the middle phenomenon. As you can see here, the accuracy of retrieving information from a document in the context is different, depending on where that information is. At the beginning, the accuracy is pretty good. Similarly, the accuracy at the end is fine as well. But the information in the middle of the context is the most difficult for the LLM to recall correctly. To combat this, we need to use a special kind of prompt-based learning called Retrieval Augmented Generation, RAG. This is also where we started our project, basically our first step in trying to create an expert model beyond just zero-shot prompt and basic in-prompt learning. RAG works by essentially creating a smart retrieval program that only adds a specific relevant piece of information from a very large text database alongside the user's question to the context of the LLM. This way you can have a text database much larger than the allowed context window, and only a small relevant part of this data is passed into the context at a time. On the left, you can see that the retriever looks at the user's input to determine what additional relevant information from the database to send to the LLM. The original text database will be transformed into a database of vector embeddings to be easily searchable. The smart retriever will also turn the user question into vector embeddings, and it will use it to find information in the data that are similar or close to your question. On the right, you can see a visualization of a few simple three-dimensional word embeddings. Words with similar or related semantic meanings will be physically closer in that multi-dimensional embedding space. RAG can often generate pretty good results. The LLM will generate the response based on the accurate information the retriever found. Unfortunately, this does not always work. The retriever may not always find the most relevant information. For example, a topic or a word may be mentioned too many times throughout the entire DDR5 spec. It is very challenging for the retriever to locate the exact relevant info. The solution we choose approached the goal in a completely different manner. It was to utilize the code generation ability of an LLM to handle all the numbers in our data, and manually create a clear guideline on the exact steps the LLM needs to perform to complete a certain task. This is the first time that we saw some success in our journey. Writing code is a strong suit of an LLM. Even small and simple models can write high-quality and often directly executable code. Existing Python libraries such as Pandas can easily handle a lot of data with only a few lines of code. The task we tried to teach the LLM was to detect a protocol violation in DDR5 traffic. Here is a very lengthy and detailed prompt we prepared for the LLM. Please feel free to pause the video to take a look. The instructions for the task were very clearly stated. All the acronyms were explained, and examples were included in the prompt to maximize understanding. Together with the prompt, we provided a sample dataset for the LLM to work with. On the right, we have the captured data of some DDR5 traffic. I removed most of it just to show the two back-to-back read commands to the same back group. On the left is a table for some DDR5 timing parameters for different frequencies. Both are crucial for the LLM to complete the violation detecting program. We initially tried to use the GPT API to directly generate executable Python code and use the exec function to run the generated code. But not too long into the project, OpenAI released their code interpreter program, which simplified the process by a lot. Considering the complexity of the instruction, sometimes the LLM may not get the Python code completely correct the first time. But the beauty of the code interpreter is that it will also see the output of the error message of the program. It can go back to adjust the code based on what error message it sees. We were also able to continue chatting with the LLM to provide more guidance on the learning until it could detect the protocol violation correctly. We gradually increased the complexity of the instruction in the chat by adding more details. For example, initially we said in the prompt that as long as the two read commands to the same bank group are less than 12 states apart, it is considered a TCCDL violation. But this is only true for a certain speed. TCCDL timing limit is based on the transfer rate of the DRAM. So we also uploaded the table from last slide to the code interpreter. It was able to understand it and incorporated that table into the Python program. In the end, we taught the code interpreter to find 5 different kinds of protocol violations. It made one Python function for each of the 5 timing parameters. When prompted with natural language like, please help me find TRCD violation in this data, it will understand and execute the corresponding function. You can also ask it to find more than one violation at a time and it will usually work. So at this stage, we have successfully taught an LLM to help us do some simple data analysis. But there's a major catch. Prompt-based learning is transient, constrained to a single session and the context. Once the context is exceeded, or if you open a new session, all the learning will be gone. So the only way forward was to save the Python function it generated locally. We then proceeded to create an LLM frontend where we used the function calling feature in OpenAI's API to extract the information in a user's prompt to intelligently determine which Python function it should call. In the end, this would function like the LLM that we taught previously, where it could understand users' natural language questions and resolve the issue for us. But in this approach, the function calling LLM has zero idea what the functions are about and have no fundamental understanding in the subject. It is only there to select which function it should run. At this stage, we have a functional program, but we barely scratch the surface of the potential of LLM with this approach. LLM was functioning essentially as a software development accelerator here. We started to look for other means of teaching the LLM, which brought us to model fine-tuning. From now on, things will get more interesting. This is where most of our effort was spent in this project. The process of fine-tuning an LLM is very similar to training the model. The difference being when fine-tuning a model, only a tiny amount of data is used compared to the amount of data used to train a model from scratch. This makes fine-tuning a lot faster than training things from scratch. It is doable with consumer-level hardware and can be done within a few hours or days, depending on the data size, the model, and the hardware used. In general, there are two ways of fine-tuning a model. You can either tune all of the parameters of an LLM, called full parameter fine-tune, or only tune a small part of the parameters, known as parameter efficient fine-tune, PEFT. A full parameter fine-tune can achieve the highest level of performance when done well, but it suffers from a few issues. First, it needs a lot of compute resources, and it also needs a significant amount of data relative to parameter efficient fine-tune. When all parameters are being fine-tuned, it is also likely to be influenced by a phenomenon called catastrophic forgetting, where past knowledge gained during pre-training becomes overwritten by the fine-tune. Parameter-efficient fine-tune, on the other hand, either adds small additional adapter neural networks to the model and tune only the parameter of those, like the one in the middle of this picture, or it can just fine-tune a small part of the existing model's parameter, like the LoRa technique on the left of the picture. This is often a very small percentage of the network. These parameter-efficient fine-tune methods might not have the best possible performance, but they are highly efficient in compute resources and need only a small amount of data to train. In short, LoRa's are easier to train and easier to inference. The performance is also on par with adapter networks, so we went with LoRa's to fine-tune our model. Although LoRa requires much less data to fine-tune, the more data we have is still better. Also, we not only need more data, the most important part is in fact to have quality data. Like I mentioned before, numerous research has shown that the performance of LLM is highly correlated to the quality of the training data. Consider our goal is teaching LLM all things about DDR5, we will need a substantial amount of data regarding DDR5. The use case of LLM AI is often answering a question or response to an instruction from the user. So the data must also be in the format of a question and a response. There was no such kind of data available openly, so the only way forward was for us to create our own dataset. It was almost impossible for us to generate an acceptable amount of data manually in a reasonable amount of time. As data efficient LoRa is, it will still require tens of thousands of data points to fully comprehend the complexity of DDR5 spec. There are simply too many aspects to DDR5 to be covered. So naturally, we look into generating synthetic fine-tuning data with LLMs. This is the core part of our project. If we can have a quality in-house dataset on all things about DDR5, we can keep using and add on to this dataset to be fine-tuned with any new model that comes out. An LLM will be given a piece of information from the DDR5 spec or some other truthful source, and based on that piece of information, it should come up with a bunch of questions and answers revolving around that topic. We are essentially using this LLM to paraphrase this source data into hundreds of questions and response pairs. This way, the already diverse information in the original text are presented to the LLM that will be fine-tuned in many different shapes and forms. This can really help the model to learn about the information. First step of generating this synthetic training dataset is to have a good set of source data material. We collected those from the internet and used the JEDEC spec. These raw data are often not exactly machine learning friendly. By that, I mean they are not structured and contain unnecessary information. So we had to manually remove all characters and symbols that would break our program, remove irrelevant data, and reformat them into a structured fashion. After we cleaned up the source text data from the spec and the internet, we also parsed most of the tables from the spec and combined them with the text data. The text will also refer to the corresponding table so that the data generated will be full of technical details. The synthetic data we wish to generate must also be in a very well-structured format. This is often referred to as the prompt template. Here is a good example of a template: a chat between a human and an assistant. We will then put a question in the question bracket, answer in the answer bracket. When using the LLM, the answer part are of course blank, and the LLM will need to generate those. Below is the prompt I used to ask an LLM to generate synthetic data for me. I asked it to generate the data in the form of a Python list and output only such data, and say nothing else. This will make parsing the LLM output much easier. A Python list can be easily parsed into any prompt template you want. Here is an example data point generated by the LLM. It is simply a Python list with two elements, one question and one response to that question. Output like these are then parsed into the desired prompt template format. Here you can see the human and assistant tag are added to the question and the response. In the end, around 90,000 pairs of questions and responses were generated. Here is a rough breakdown of the composition of the dataset. It covers most of the sections of the specs for DDR5 DRAM and RCD, plus some helpful relevant data from the internet. This does not cover all of the sections yet. We are planning to add more data to this in the future. Please feel free to pause the video to take a closer look. Here is a block diagram for our data generator. You can pause the video to take a closer look. Please also feel free to see the paper we wrote regarding the details of our data generation program. At the moment, it is still a bit basic, but we are planning to overhaul the program to generate data other than simple instruction and response pairs. The next step of the journey is to find a way to actually implement the fine-tuning, both the software and hardware side of fine-tuning. Let's first talk about the hardware. Although we reduce the hardware requirements by using LoRa fine-tuning technique, we still need a good amount of compute power to do the fine-tuning in a reasonable amount of time. The model will also need to be fitted in the memory of the GPU, and LoRa does not reduce memory usage. Training neural network also requires very high memory bandwidth. Slow memory will become a major bottleneck and prolong the training time. So we not only need a lot of memory, but also very fast memory. We settled on renting 3 NVIDIA A100 GPUs from cloud compute providers. Each is equipped with 40 GB of super-fast high-bandwidth memory with 2 TB of bandwidth. Each is capable over 300 TB FP16 flops. This was a very costly setup and it was very difficult to find availability, but it really helped us experimenting with different settings and configurations. We are planning to eventually build our own GPU cluster locally in the future. For software, we chose libraries made by Hugging Face. There are lots of tutorials and guides, and lots of support on how to best conduct the fine-tune, which was very important for us hardware engineers. It was a relatively painless process of figuring out how everything works after trying out a few examples. We splitted the dataset into a training dataset and a validation dataset with a 95:5 ratio. Having a validation dataset can help regulate the training of a neural network very well. You will be able to see when the model starts to overfit and stop the training accordingly. Here are some important parameters we tweaked to achieve the best results. For the LoRa parameters, R is the rank of the small matrix we fine-tune. 512 is quite high for LoRa, but the higher it is, the better the LoRa can understand the complex relations of DDR5 concepts. Alpha value is essentially used to calculate the gain of the LoRa. Twice the rank would mean the LoRa parameters are 2 times weighted to emphasize the learning in the LoRa. LoRa dropout being 0.1 means during the training, 10% of the neurons are randomly selected to be not included in the training, so that not a single or a few neurons become overly relied upon during training. For the trainer parameters, we went with very standard values. The batch size was determined based on our memory constraint on the GPU we choose. and the gradient accumulation of 16 was used to mitigate our small batch size. When choosing a base LLM to fine-tune, here are some of the things that we wanted to see. First, it should have a relatively small parameter size, so we can fit it in the GPU and move quickly and flexibly to experiment with different settings. Second, it needs to have a good baseline performance in instruction following. Finally, it should have an open licensing, so if it eventually reaches production level quality, we can easily integrate it into our product lines. Around that time was when Mistral 7B model was first released. It was the best 7B model at the time, and it beats a lot of larger 13B or even 33B models, so we use it for our experiments. Later in the project, we also tried the E34B. It was a lot larger and it performed quite well, while still fitting in our GPUs. Here is a loss curve of one of our training experiments. You can see that the blue line keeps decreasing as we train more and more, but the validation loss line flatlines earlier, indicating that the further training will cause overfit and reduce the model's ability in generalizing. To evaluate the performance of the model, we created a DDR5 quiz that consists of 20 questions. The questions are never seen by our fine-tuned model. We compare the results between the baseline model, the fine-tuned model, and GPT-4. The evaluation was done with zero-shot prompt questions only. We saw that the baseline model was hallucinating terribly. GPT-4 was able to answer some questions mostly correct about DRAM, but has no idea what an RCD is. The fine-tuned model answered the questions quite well, going into deeper details than GPT-4, and remaining mostly truthful. I understand this evaluation process is quite subjective. We are still working on creating a more systematic, automated, and broad evaluation program. Let's now take a look at how the model actually performs. I have everything set up and ready to go here. The baseline model we used is E34B. Before we begin, please keep in mind this is still a very early proof of concept model, and we are still actively working on it. Now let's ask a few DDR5 questions. So I have 5 questions prepared, and I will ask each of them, and I will go over the results after it answers all of them. So the first question is, what is a DDR5 RDIMM and what is the DDR5 RCD? The next question, what is ODT? So the third question, what does X4, X8 mean in DDR5 SDRAM X1 and X8? So next question, what is validation pass-through mode in DDR5 RCD? So now the last question, what is the self-refresh mode in DDR5? So now it finished generating the answers. Feel free to pause the video and take a closer look. Most information was pretty accurate and truthful. You might have noticed that some of the answers it generated are relatively shallow and often not technical or detailed enough. Well, this is something we're currently working on to improve. Out of these responses, I think the last one for self-refresh could use some work. It got most things right, but the last part about power supply stability was hallucinated. Remember that LLM only get one shot at answering a question. The answers are always generated based on the first thought it had. As humans have ability to think about things in our head before speaking out loud, so we should also give the LLM a few more chances to reach the final conclusion. We can do it manually by asking the AI to regenerate a response for this question. So now the last reply was removed, we can ask this question again. This time it gave me a more detailed and truthful answer. This technique can be automated and the LLM can choose the best results out of many responses it generated. I will talk about this later on. Now that we have seen the model perform, here are some of the next steps we are planning to take in the project. One of the most important things we would like to do next is to further enhance our dataset. Currently, the dataset is too homogeneous, consisting of only one type of data and limited amount of topics. We want to first include more topics, cover more aspects of DDR5, DDR5 RCD, and other DDR and memory generations, and most importantly, also information about our products. In the end, we would like to perhaps include information regarding other communication protocols as well. Hopefully, we can also integrate the content of a few EE textbooks into the dataset. Having diverse data can really help the model generalize. We also wish to add more human feedback. This will be done by first having a lot of users interacting with the model, and essentially writing down the strengths and the weakness of the model. Knowing the weakness of the model and the mistakes it made, we can go back into the dataset and adjust the data and retrain to improve the performance. We also want to add the DDR5 capture data into the training in some way, so the model will have a good understanding of the data naturally, rather than needing a Python script to detect them. The next thing we think is very important to do is to do better on RAG. We made some shallow attempts and there are definitely potentials in combining RAG with a fine-tuned model. But more work is necessary to understand what goes behind the RAG libraries. We might also need to fine-tune the embedding of the RAG so it has a more focused connection on the relationships between words frequently used in our domains. Also, like I mentioned before, we will need to develop a more sophisticated evaluation mechanism. The current 20 questions give us a good feeling on how well the system performs, but it is hard to compare them. So we are considering making a multiple choice-based evaluation with more questions that covers more topics. The chance of getting a correct answer plus correct procedure of reaching the answer will be the score of a model. With a metric like this, we wish to compare the impacts of each LoRa settings, trainer settings, different baseline models, and different prompt format, and etc. We're also planning to try a larger model and more complex baseline models in the future. Advanced prompting techniques such as chain-up thoughts and tree-up thoughts are also things we're planning to look into. These techniques use little-to-no training and can greatly improve the performance of a model by many times. The model will be given chances to actually think about their answers before giving them to us. It is, however, not very straightforward to implement. A bit of fine-tuning could be necessary to make the model understand how to do chain-up thoughts and tree-up thoughts. In conclusion, at this stage we think we have a pretty solid DDR5 expert AI model. It is still far from complete or near production level. This is still very much an ongoing project for us. The field of artificial intelligence is also moving forward at an incredible pace, with a lot of research being done and many new techniques being discovered every day. We have a lot of things planned in the future to improve the system. Thank you so much for your attention.